Planets and moons this large are sorted by their density, with that metal in the core and the rocky crust on the outside. But that's not how they started out. They started out with those components finely mixed together, and that's what our chondrite is. Chondrites are a kind of cosmic dust bunny. They're everything that was floating around in the disk of gas and dust that the sun and the planets formed from. So they're clumps of everything that was floating around, including the metal, rock, even ices as well. Now you can see that these are mostly made of rock, but you can see the metal in there as well. Now that's iron, which is what the core is mostly made of. Now in some of these, we also have quite a lot of water. In this one here, this is called the Murchison meteorite, a CM chondrite that fell actually in the same year that the moon landing happened in Victoria, 1969. And this one has up to 10% weight water. So it's a huge amount of water in this, as well as a lot of organic chemicals, with chemistry as complex as amino acids, which are the building blocks of proteins. So the building blocks for life are in these really primitive meteorites from the early solar system. Now another thing that may have been going into the ingredients, the mix of things that were building the Earth, were comets. Unfortunately, I don't have a piece of a comet to show you. There's no pieces that we know of that have survived entry into the atmosphere because they're mostly made of water ice. So they probably exploded when they do enter the atmosphere. And that may actually be what the Tunguska explosion was in Siberia. And that was a giant explosion that flattened trees for kilometers. And that may have been something like a comet exploding in the atmosphere. But we don't have pieces to show you of that. But that might be where the water component is coming from. Now the rocky part of the meteorite contains radioactive elements, including uranium, thorium, potassium, and originally they would have also contained a radioactive form of aluminium. And the metal would have contained a radioactive form of iron. Now, these are not dangerous in the concentrations in the rocks today. And they wouldn't have even been then in a rock this size. But if you put enough of them together, so we're building a baby planet, we're throwing all these chondritic materials, these undifferentiated clumps together. Once we get a ball that's bigger than about a few tens of kilometers, the heat inside that those radioisotopes are giving off as they decay can't escape. So in the core, the center of that begins to heat up. Just like if you were wrapped in too many blankets, you're the source of heat, it's not going anywhere, you need to get out. And that's what this heat does. It starts to heat up and it starts to actually melt the inside of it. Add to that the early solar system is a very chaotic and very busy place. Things are flying around. The gas giants are still moving in their orbits. They're still shifting. And that results in huge amounts of impacts. So as well as heat from the inside, there are large objects slamming in to protoplanets, to our baby planets from the outside. So heat's being added from the inside and the outside to any planet that was forming. So things inside our baby protoplanet start to melt. Things like the metal start to stick together and form droplets and start to sink towards the center of the body. So the gravity of the whole thing is pulling them towards the center, and they're kind of dripping through the entire body. And as those molten drops are seeping through the body, they begin to form the core. Likewise, the volatiles, the ices, the water, things like that are bubbling upwards into the outer layers of the body. So we start to get a differentiated protoplanet. So the smallest differentiated world that we know of is well, we call it an asteroid, but it may be better to call it a remnant protoplanet. It's an object left over from this period of formation named Vesta. And it's a tiny little world, but it's big enough to have separated into a core and a crust structure.